All right, welcome everybody to the final data structure of CSI 41 data structures. This is the ultimate data structure, ultimate in the sense that it's the last one. There it is. That's the data structure. A data structure is anything that holds lots of variables, right? An integer holds 32 bits, and so you can treat an integer as an array of 32 booleans, or 32 bits. So this is, in fact, a data structure. Now we want to initialize our data structure properly, so we'll do this, and we're going to hold 32 booleans, all of which are false. There we go. I know. Like you thought, the only data structure you learned in CSI 40 was arrays and vectors, but nope, integers are data structures too. If you want to hold 64 booleans, you can do a long, that holds 64 that way. So you can individually read and write to each one of these bits, okay? And in order to understand that, you first kind of have to understand how binary works. So in C++, in modern C++, you can actually write the bits using the following syntax. I could write 000, 000, 000, 000, 16, 20, 24, 28, 32. Got carpal tunnel now, but there it is. That's exactly the same thing as if I typed integer x equals 0. I think I counted that out right. Yeah. So that is 32 bits, all of which are 0. The apostrophes, as always, don't do anything. They're just there to help break it up so that you can kind of look at it in groups of 4. Now, if we were to see out x to the screen, what do you guys think this is going to print to the screen? Oh, you're right. It's just 0. Now, we can set each of these bits individually to 1s. Right? If we try setting it to a 4, that's just not going to work. But a 1, we can set any of these guys to a 1. And so the way that it works in binary is the rightmost digit is the 1's digit. This one is the 2's digit. I can type right. This one here is the 4's digit, and so on and so forth. So you can make basically any number within your binary range by setting different bits to be true and false. For example, if we were to echo this, it would print out 4 to the screen. If we were to add 1 in the 8's digit, this would be 8 plus 4 is 12. If we add a 1 in the 1's digit, we're going to get if I compile it, we'll get a 13, and so on and so forth. Now, this is a lot of headache to write. And so usually what we do is we'll write big, long, stupid binary numbers like this using hexadecimal. So 1, 2, 3, 4. 1, 2, 3, and that is 8 plus 4 plus 1. Sounds to me like 13, which is A, B, C, D. And so if we see out X and we see out Y, you'll see we get the same number. Now, all of these leading zeros can be dropped, so I can actually just do this if I wanted, and it's still 13. Okay. So, do you guys see how this integer here is like an array of 32 booleans, 32 trues and falses? Does that kind of make sense to you? And so the way that we grab individual bits and set individual bits are using what are called bitwise operators. And you might have seen these before, especially if you were making a mistake. And you did something like, let's output x to the yth power. Now we're going to need parentheses around this because there's actually an order of operations issue here. The double left arrow operator is the left shift operator. It's a bitwise operator itself. And so there you actually will run into order of operations problems So just slap a parentheses around it. And so you might think, okay, well, we're going to take 13 to the 13th power now, right? Right? And we get 0. It's not exponentiation at all. It is a bitwise operator, okay? Before we get to that, though, let's actually... I'm gonna cut this down to size. This is way too many digits to deal with. I'm gonna cut it down to a char, I guess, in size. Everything that I don't type is a 0, so I can just leave it at this if I want. So now let's even take it down to a nibble. A nibble is a half byte. Did you guys know that? A byte is 8 bits. A nibble is half a byte or 4 bits. So if I any bit I don't type, it's just a 0. It just makes things easier. Okay, and this comment is no longer valid, so let's clear that up. All right, so we're gonna have integer x, integer y, and we're gonna do, I don't know, something like this. Why not? Okay, now this is OR, but this is not the OR that you are used to. This is probably the OR that you're used to with 2 left arrows. And if you do a bool alpha here, we're going to be ORing together 13 and 7. This is the number 13, right? And this is the number 7, because the 1's digit is set, the 2's digit is set, and the 4 digit is set. So 1 plus 2 plus 4 is 7. Okay? So if we OR these two things together, what are we going to get? True or false? What are you guys saying? One person, thank you, Renee, has it correct. It's going to return true, right? Because false is 0. Everything not 0 is true, right? So if we OR together true, this is true. ORed with true, we get true. What if we AND them together? What are we going to get? It's true. They're both not 0. The only way that you would get a false out of that is if all the bits are 0, then you get false. Okay? So let's change this to a 3 or something. Now, if we do bitwise OR and bitwise AND, this is a little bit different. Bitwise is also the name of the company in downtown Fresno, right, that does a lot of tech recruiting and things like that. Bitwise AND is a single ampersand, and bitwise OR is a single vertical slash. They return an int, not a Boolean. They return an integer. And what they do is they go through every pair of bits and do the whatever operation, and, or, not, whatever. So what do I mean by that? The answer, if I do x ORed with y, look at the 2 bits above here. We got a true and we got a false. Actually, let's make this a little more interesting. There we go. Okay. So the answer we're going to get is going to be, I'm just going to write this in binary. So what is true ORed with false? So each pair of bits, each corresponding pair of bits gets ORed with each other. So instead of ORing the entire value with each other, each corresponding pair of bits is going to be ORed. So this is going to be true. And so we're going to get a 1 in this place. Now up here, we've got 2 falses. What is false ORed with false? That is also false. Good. And then we have false ORed with true. What's that? We're going through the whole truth table here. This one is also true. And then we have true ORed with true. And this one is also true. Okay. So if you ask what is 13 bitwise ORed with 3, then we're going to get 1011. That's a 1 in the 8th digit. That's a 1 in the 2's digit and a 1 in the 1's digit. So this is going to be equal to 13. Okay. And this will confuse the hell out of you if 13 bitwise ORed with 3 is 11. No, sorry. It wasn't 13. Sorry. It does confuse you. Right. It's a 9. That makes a little more sense. Okay. So I had the comment there from before. Okay. So 9 bitwise ORed with 3 equals 11. Okay. And so this is CSI 1. Yeah, this is CSI 1 knowledge. We do a lot of truth tables in there. So 3 bitwise ORed with 9 is 11. And people are like, why isn't it 12? Well, we're not doing addition. What we're doing is we're going through every pair of bits and we are ORing them together. All right. And if we did AND here, if we did AND instead, then we will do an AND on these two things. So what is true ANDed with false? What is true ANDed with false? It is false, and then false ANDed with false is false. Good. False ANDed with true is false. Good. And then true ANDed with true is true. Good. So 9 ANDed with 3 is 1. Okay. And again, this will confuse the hell out of you if you're thinking of them as numbers, but they're really not numbers. You really want to think of these as bit fields. Okay. They are a data structure. They are 32 bits, and we're just doing operations in parallel on all 32 of them. This is 32 times faster than using 32 different Boolean operations, Boolean variables with Boolean operators on them. So if we say what is 9 ANDed with 3, we get 1. Okay. So what other operations are there? There is XOR, which is, again, this is not exponentiation. 9 to the 3rd power, not that. You have to use POW if you want to use exponentiation. This is not exponent. This is XOR. So XOR is true when one or the other, but not both, are true. So you have one true, but not two trues. Okay? If you have two trues, it's false. So let's go through this. So what is true XORed? What is true XORed with false? True. Okay. What is false XORed with false? And XOR, by the way, is the OR that you use when your mom is like asking you, hey, do you want pizza or sushi for dinner? A lot of jokers will be like, yes, because they're used to the inclusive OR, which is the OR we normally use in logic. But when your mom's usually using OR and putting a little stress on it, that means exclusive OR. You get one or the other, but not both. Okay? Either clean your room or you get punishment. That's, your kid would get mad at you, right? If they clean the room and you punish them, right? It's exclusive. It's one or the other, but not both. Okay? So false, XOR with false is false. Would you like your super solid? Yes. That is what logicians say. But in English, we determine the difference between inclusive and exclusive OR by stressing it. We'll say, do you want soup or salad? By putting a downbeat on it, we mean it's exclusive. You get one or the other, but not both. Yep. So false XORed with true is, in fact, true. Good. And then true XORed with true is what? What do you get if you XOR true and true together? Mm-hmm. So, you ever wonder why CSI 40 students get confused by exponentiation? They're like, I took 9 to the 3rd power and I got 10. Would you like a soup or a salad? Yeah, and they're like, it doesn't make sense. Like, I don't understand what's happening. It's like, yeah, it's because it's not exponentiation at all. It is XORing. And so you can think of XOR, an easy way of doing XOR is if you have a 0, leave it alone. So whatever you have before, we have 2 zeros here, so we just leave the 10 here alone. And if you have a 1, you flip the bit. So here we have two ones, so we're going to flip these bits. So the 0 becomes a 1, the 1 becomes a 0. So 1 means flip the bit, 0 means leave the bit alone. That's the easiest way of doing XORs. Okay? And so there's one other operation, and then we'll call it for today. And that is not. And so not is indicated using the cheat code character, so the tilde. We don't need y anymore. Oh, deleted too much. Sorry. We don't need y anymore. And so if we flip all of the bits in x, what do you think we're going to get? The ones become zeros. The zeros become ones. 0, 1, 1, 0. So we should get what? What number? 6. Right? But what we actually get is -10. And the reason for that is because you know how we forgot about all those leading zeros that we had before? We had all these zeros. All those guys have turned into ones also. So, so it's not actually 6. It would be if we only had four bits like this. But all those other zeros turned into ones also. Now you might be wondering, like, wait a second, how did I get -10 out of this? And the answer to that is really a CSI 45 topic, but I can give you the 1-minute overview of it. So there's something called 2's complement, and this is how we hold negative numbers in integers. It's different in floating point numbers. With 2's complement, the highest bit is equal to the, just give me a graph, go on. This is all way too mathy. The highest bit is equal to the negative of what it should be. Yeah, none of these guys are explaining it clearly, huh? Okay. So let's say we just had 4 bits here. The first bit here, is the 8's bit, the 4's bit, the 2's bit, and the 1's bit, right? That's why this is 9, right? You have 1 plus 8 is 9. And if we put a 2 in here, it would be 11, right? So we would have a 1 plus a 2 plus an 8 is 11. You guys understand binary? Put them all in here, we get a 15. So you just add all the digits together. This is the 1's bit, the 2's bit, the 4's bit, the 8's bit. With negative numbers, you would have a -8 as the top bit. And so all ones here would actually be -1. Because you have -8 plus 4 plus 2 plus 1. 1 plus 2 plus 4 is 7. 7 plus -8 is -1. And so no matter how many bits you have in a number, if you have all ones, then it is -1. Because the biggest digit is 1 greater in magnitude than the sum of all of the smaller ones. And so if you have a 32-bit number, the biggest, most important, most significant bit is worth 2.1 billion and change. And if you have all ones, then it'll all add up to exactly -1. So if we, in fact, just made this guy 0 here, and we outputted the inverse of it, we're going to get -1. Okay. So if we inverse this, we'll get -2, because the last bit is 0. So it's 1 below -1. That's the 1-minute explanation of it. Okay. So just the highest bit. If the highest bit was worth -128, if the highest bit was worth 128, and if you have a signed integer, it's worth -128. Then everything else is the same. You guys with me on that? You don't really have to worry about that for this class. That's more of a CSI 45 topic. But does that kind of make sense? Like the most significant bit's just worth negative what it should be. Ish. All right. Then, okay, we'll do a couple exercises then. We have -8-bit, the 4-bit, the 2-bit, the 1-bit. So what is this number? If we're just going to output X. Nothing, nobody's been bitwise inverted. What value is this? 5. Do you guys concur? Yeah? Like, we're just talking about 4-bit numbers now. We're not even talking about 32-bit numbers. We're just talking about 4-bit numbers to keep things simple. You concur? Excellent. What about now? What value is this? -8 bit set, the 4-bit set, and the 1-bit set. What is -8 plus 4 plus 1? The tilde is not messing. The tilde is bitwise not. So all the trues become falses, all the falses become true. So, yeah, this is -3, okay? And so if we were to invert -3, it would become 2 in this case, right? Because the zeros become 1s and the 1s would become 0s. You guys see that? So all the 1s become 0s. He that is first shall become last. He that is last shall become first. So the bitwise inverse of 2 is -3. The bitwise inverse of -3 is 2 in our little 4-bit world here. Okay? And so if you have a 32-bit number like this, then this is going to be all 1s after you invert it, right? We're going to invert it. It's all 1s, which is going to be -1, except for the 2's bit. The 2's bit's going to be false, right? It's going to look something like this. Like it's going to be all 1s. I'm not counting, by the way, with a 0 in the 2's bit and a 1 in the 1's bit, right? If we flip this, because it's an integer, right? So what's going to happen is this will be -1 minus 2. And so this is going to print out -3. See that? And so the inverse of -3 is, in fact, 2. And 2 is the inverse of -3, even with 32 bits. Like, when you have this many 1s, like, you don't count them. You just say, okay, if all 1s is -1, this is -2. Right? All 1s is -1, so if you subtract 1 from it, -2. -3, -4, -5, -6, -7, -8. Yep. Oh, I didn't actually change the number, but yeah. That is that. And that's where we're going to leave it for today. And so we will show you guys how to individually set and test how to insert, search, and delete into the world's most ultimate data structure, the integer, on Friday. All right, stay tuned for that. These are actually very useful. They come up a lot in computer science. So you need to have some, you need to have a great deal of proficiency in order to do a lot of stuff. Then manif open. And you'll just see things. You see all these like bitwise OR operators and stuff like that. Like you need to know this because it's used. Like this is the documentation. Like when you pass in options, a lot of times you just pass in an integer, and it just uses the 32 bits of the integer. True, false. Is this option set? Is this option set? No. Yes. No. Yes. And so it just uses a integer to hold up to 32 options for a function. So yeah, like Hazelton says, it comes up all the time. And so you gotta develop your proficiency with them, and they're kind of a fun data structure to play with because it's an integer. It's your most boring variable ever. Okay, so that is it for today, guys. I will see you guys on Friday. Keep working on the Pascal assignment, and stay safe. Peace.